parts that we will cover. It's a nonlinear analysis of trust. Okay, I think for coming Monday and the week after are all public holiday. So that's why to speed up and finish this lecture first. And then I think the week after next week, then we shall have hands-on sessions. Okay. And okay, before I go on, I think still give you some recap. Give you the flavor how do you do the red lab scripting to solve the finite element. Okay, which I will show you. Before we move on to the more complex one. So later on the NC session, you have the opportunity to run the thing. Okay, let's show you how we do the solution symbolically. Okay, you have the okay. So if you now have these command, when you are defining the script in you see this command? This command is defining symbolic variable. And then when you type the stiffness, okay, in the MATLAB, you can define the matrix by having a square bracket. Comma is to separate the column. Semicolon is to separate the row. Okay? So you see, by defining this, you have stiffness A1. And then next, you define the second stiffness. Again, symbolically. So you have K2 minus K2 minus K2, K2. Okay. And then the next step you have to define is defining the force on each 3D degree of freedom. Okay. So in this case, what are the boundary? What are the degree of freedom? So you have, remember the question we had just now? This is the one, two, three. Okay? If the first element is K1, the second element is K2. You have stiffness matrix for the first element, stiffness matrix for the second element, but you still have to define where is the free degree of freedom. So you might have U1 fixed, you might have your U2 free to move, and you might have U3 free to move under the cooling. So what shall we define? We shall define 3 degrees of freedom. And then Then you have to define the knot element association. First row is for first element. It has first degree of freedom and second degree of freedom. So your first element is element 1. It has 1, 2 associated. How about the second element? You have 2, 3 associated. These are all the index telluric association. And then, what's next? If one of the, because this combination of 3 by 3 stiffness is going to be singular, you're going to truncate away the free degree of freedom. So you see here, you have K1 plus K2 minus K2 minus K2. This is a truncated one. What was the full one? The full one was K-net 1, 1, K-net row 1, 0, and then this one is second row. This is the K-net 1, K-net 2, 2, this one. And then lastly, so this is the full matrix. You see this? This is a full matrix, but this is singular. It cannot be inverted. Okay? In order to do the solution, you are talking about the K-net truncated. So you are kind of like square out this 2 by 2 matrix. And then finally, what do you have to do? Find the force acting on the free nodes. It is not 2 and not 3, which is free. And the force is acting on E. So this is 0 E. And then, how do you do the solution? In MATLAB, the inversion is just K-net truncate. It's almost a division. Okay. It's also truncated. These are the free degree of freedom. Okay. Of course, in MATLAB, you can also do the other way. You can write in inversion of the stiffness matrix times F max. Yep. You're going to obtain the same solution. It is the INV for inverse. So both are working the same. Yeah, if you do write this, this one, yeah, you go back and find out. Then we now move on to something non-linear. Okay. So linear analysis is for small displacement. Okay. We are talking about small. We are talking about small strength between 0.1 to 0.05%. This works perfectly for steel structure. Okay. It doesn't work for rubber. It doesn't work for plastic. So when and they require the stress-strain proportionality within the linear elasticity. And also assume that the force don't change in direction. You assume that the support is always there and not changing. Okay? However, in some cases, as you apply the force, the boundary might change, the structural shape might change. Okay, the structure might lose the stiffness or buckles, and you might have displacement. And next we will cover the geometrical nonlinearity as well. Take for example, the structure might not behave linearly, okay, when you have hinge formation. So let's take an example. If you now look at these spring-supported rod, okay, how do you describe the motion? Okay, because it's torsional spring support. So as you bend the rigid bar by angle theta, the torsional spring will provide an opposition moment, which is k theta. So let's imagine if this is a rod representing the door. If the door hinge is a spring, okay, then you can have the spring back. So this torsional moment is k theta. The higher the angle of the rotation, the higher the moment. And then when you apply the force on the door knob, okay, if you apply that force in constant direction, you can find that as the door opens, the external moment reduces. Why? Because the moment arm that is between the applied force to the door hinge is shortened in the moment arm. The moment arm is the door length times the cosine theta. Okay? So if that's the case, the simple assumption applied moment FL is k theta is giving you an underestimation of the rotation. Okay? On the other hand, if you account for the moment arm change, because the moment arm is this length, okay? This one, when the door rotates, the door width doesn't change. This is still L, but the moment arm change. Right, the moment arm, there's the dash one. You see that？ 还有你们一般看的那个课本，一般都不画图，那为什么？画图比打字难。所以，但是你自己要解题的时候，你一定要画图画够比较好。你如果什么都不画，那你就自求多福，因为你的答案不见得就是解当下你要到 的，不见得会在考试再出现。它可能转一个90度，转一个60度，从水平那边垂直，那你很可能就那个答案就写错。即便是这幅哈。So the important thing here is you must be able to draw out your model. Okay. So the previous model is what was the previous model? The previous model is assuming if you assume theta is small. This is approximated to FL. So this is the kind of assumption that you get linear range. But if you are not assuming small angle, you can see that the stiffness of the structure of the door hinge will go very high. So meaning you can't even close the door with a given force anymore. Okay. 就像这种上 ，x 轴是角度 ，y 轴是这个引力，这个扭力。小力的一个假设。So why we need to spend time on this? So to give you the understanding what happened. Okay. So this is the illustration that when you are approaching that big angle, you need greater moment to achieve the same starting moment. So this is the big difference. Okay. Then next, let's talk about the buckling. Buckling is similar to the previous question, except now the bar is standing up, not horizontal. So you still have the rigid bar and you still have the torsional support and the anchor. So now the free body force diagram is shown here. Okay. But now what is the moment now? 同学，这道题也是跟刚才有过，你一定要把你的几何画好。你说画任何东西，那你就没有办法解题了。你看这道题如果画角度，那你怎么解？刚才的第一角跟现在的第一角一样，来。Okay, this is the angle of rotation for a vertical column. Column is is the one that supports vertical force。所以这个是一个柱子的模型，刚才是悬臂的，现在是一个柱子。同学最近有没有看到新闻？在某一个工地，在盖楼之前打地基，打地基的这个柱子要绑钢筋，有没有听过这新闻？是哪里的这个地基？钢筋照理是立着，然后你们要绑一下，然后再灌水。所以某工地做了什么事情？某工地这个柱子的位置错了，结果他把钢筋凹一下。那为什么熬完这个钢筋还能做柱子呢？熬完这个钢筋就是这样 ，OK， 那你会降低你的承重能力，那你可能会错觉。So this is kind of understanding on the mechanics. It may start from the same vertical position. If you bend this is equivalent to a torsional spring. Or in short, this is a hinge. A structure is structure when there is no hinge. When there is hinge development, this becomes a mechanism. Okay? So to say, you see now, I'm still writing the balance equation. But because of a moment difference, this force is supposed to be supported by the column stiffness. Okay, but if it happens that the column give way, a column should remain vertical. If the column gives way, then it will start rotation. This rotation is unwanted. Why? Because the vertical force acting on the column. If this is one story of the building, if this is the force applied, what's the difference here? Given the same force. Previously is going through the axis, there are no moment because there are no offset. But if now the force going through the axis is offset by a distance delta away from the support, this becomes a hinge. Okay? And this hinge, okay, what happened? Will cause a collapse. Okay? So when the collapse is going to happen? So if you find a limiting case, a certain angle, okay, this is going to be equal to 1. Okay? 所以同学看到没有？这个表示什么？你在特定的这个角度下，它可能就会撑不起这个重量，然后它就滑下来。Okay. So this is understanding. Okay, you can see here. So if they come to balance, but at small angle already, theta divided by sine theta is equal to 1 at small angle. So as a result, you can see the balance. Both sides have theta. So you can see that the critical loading is the applied force times the length is equal to the stiffness. So this is the critical loading. 所以那个柱子越长，那个零件的这个压缩力就越小；柱子越短，那零件压缩力就更长。And then also, if you are analyzing the buckling of the linear bar, okay, you can see this effect. Consider now a pin support bar resting on the linear spring. Okay, when compressed by horizontal force, okay, the spring is undeformed. Okay. In this case, there also exists a critical load that the bar will be put at this is also sort like a bubbling。所以看到没有？你那个错举不全然停止3举之中，那你都转90度，这跟刚才的题目一样，因为是水平的，这个水平感，那受水平的力，那你就会也是一样发生错举。对，看到没有？那个题目怎么办呢？我教你可能教你90度垂直的压力，然后再教你水平的0度的在水平压力，那一样会出现错水，答案是一样。And then for today, because we are not going to handle some vertical and horizontal bar, we're going more complex. We're going to talk about how a horizontal bar can support vertical loading. In this case, it's not buckling, but it is pre-tension. A structure which are supposed to give way become stable when there is a tension. 刚才讲的是压力下的结构变机构，就错举。那我们反过来，这个结构它本来是不稳定，那你给它张力，所以这个结构突然变稳定。Okay, so let's watch a video how you have a stable cable.
So slacklining is the umbrella term for all the different facets of walking on a flat woven band. One of these facets is highlining, which is walking a slackline high off the ground. One of the best ways to train for highlining is setting up slacklines over water. When the current is passing underneath you, you automatically start to fall that same direction, and it's almost like you're not in control of your body. And that's great practice for highlining, because in highlining, when you're dealing with all the fear and adrenaline, oftentimes it feels like you're not in control of your own body either. Chamonix is a town in the Alps of France, and it's one of the places that really drives me in highlining. What's different about highlining in the Alps is that the whole experience is more intense. Being that high off the ground, you look at the valley below, the houses are just tiny specks. They look like toys. It's unbelievable. One of the highlands that I walked recently in Chamonix was on a Yukimi, and when we reached the top, it was a totally clear blue sky, and we were surrounded by peaks. But during the process of braking, the clouds started to roll in. It was like an acid trip walking the line. I was out there in space and exposure trying to balance, and the line was swinging beneath me. Meanwhile, these huge white clouds were passing, and the line would disappear, the anchor would disappear, and then it would reappear. And there was no way to control it. I just had to hang on. Yes! The beauty of the mountains is awesome, and yet it is a landscape that demands focus and respect. Alpine highlining is the purest form of the sport I can think of.
So far we have learned about structure, a simple bracket, and you can see now even a tiny rock, okay, or snake rock become a structure. Okay. So you could have seen this before, a chain structure. Under the pull by the weight, become stable to support its own weight. So this is a suspended bridge structure named catenary. Okay, and then you can also where the source of tension. The source of tension comes from gravity because the chain all got the weight act on to the chain and then pull it to this hyperbolic sine shape. And then next, you also have a cable stay structure like suspended bridge. So the cable provides the axial tension but not compression. They have almost no fracture stiffness. Okay. So now, we're going to mix the linear story. Okay. This is the geometrically unstable structure. So imagine you have two rods. Is it going to support the vertical force? No. It's going to give weight. So how can it become stable? It becomes stable when it is stress different. Okay? So let's see this example. So if the force really caused the rotation of the rod, you can already see the starting length is L. By the time the middle point is dragged down by D, how much is the new length? The new length is going to be L square plus D square, and then take the square root. So the extension then must be D over L. Okay? So in this case, so you can see what is resisting the vertical force. It is not the stiffness of the structure. What is resisting this vertical force is the bar tension. How much is the tension? We're going to check it out. But anyway, it is the bar tension. Imagine. Okay, let me draw it now. Imagine these two bars is free to rotate. Under the force P, the middle point comes down. Come down by D. So the new length is increasing. So as a result, so this two is providing a tension so as to resist the heat. So you can take this as the angle. How much is your vertical tension? If you draw this. If this hypotenuse is the vertical tension, the upper one is sine theta. You see that? Tensions along the rod is reduced into vertical component and horizontal component, and the vertical component is going to opposite the P. So as a result, you can see that, and also you can find what is the sine theta. This is the distance divided by the length. Okay? So is that right? So it is possible to solve for the equivalent statement. So you can see that the vertical force is resisted by the tension. Okay? How much is that? Yep. So this is the relationship. The applied force is 2 times the tension over L, and then V is the vertical displacement. 所以从这个简单的一个推导，你就看到什么？张力本身的效果等同于垂直感。So what does it say? It says that you apply the vertical force. Okay, the middle point deflect down. Okay, and then the spring is opposing it with a spring constant equivalent to 2T over F. 所以你预张力本身就是可以提供干。那这个是相当于是你。Okay, and then next, how do you describe this property to find out the tension? As you can see, just now, What is the new length here? The new length, if you look at this triangle, if this is the starting length and this is the new length, and this is the D. The new length is old length plus vertical diffraction. So likewise, if you want to expand the idea about the rod extension to find the tension, what you can do? You can draw what was the starting length L0. What is the new length? If the teeth is placed by U1, V1, another teeth is placed by U2, V2. So you can already find the inclinations, vertical displacement change divided by the starting length. You can also find the cosine, which is about equal to 1. And finally, can you find what is the tip force? The tip force is tension times the D over L. What is D? D is vertical displacement difference. 所以你刚才看到的，我刚才讲的 D 是什么？这个 D 是垂直位移，这是垂直位移怎么算？那刚才我们看到的是左右两边固定。所以你现在看，如果说我1节、2节、3节，然后另外一个是1节、2节，那你这个垂直位移是多少 ？In this case, it is U1 but the V1 vertical and V2 vertical. The V here is your V1 minus V2. Okay. But of course, if you now have multiple, here you have your V1, here you have your V2, here you have your V3, here you have V4. How much is the vertical displacement here? The vertical displacement is your V3 minus V2. Okay. So likewise here you have the V2 minus V1. Okay. As a result, how are you going to write your vertical force? Your vertical force, you're going to have tension. 就我们讲的这个力量，作用在这个缆线上的力量，你去拉它，这是外力，所以你的 Fx 节点力是 Ct，F2 节点2上面力是正力。看到没有？你如果画得出来，你这个公式写得出来。难点难在哪里？你如果不去画，那你就看不出来。看到没有？那我们现在来画，斜一个角度。这个时候是什么问题呢？这个力还是在垂直方向。OK， 那它的这个垂直力多少？看到没？看到没？那垂直力是 So what is the vertical force that you can support? P. You can support it by T sine theta. What is theta? It is T vertical displacement y2 minus y1 divided by the length L. Okay, with this, you can see this vertical force is upward. This vertical force is downward. Okay? Upward, downward, depending how you define. Okay? So after all, if you take the account of this, you can see other than the cable along the length. You now have the vertical force component on the two ends of the inclined cable. One negative and one positive. OK， 看到没？所以这个就是你的张力提供你的垂直等效感能力。So in a way, you can say, yeah, this is different from the cable tensions. So in short, what is the total stiffness then? The total stiffness comes now from two parts. One is the bar elongation. This is your linear stiffness. It only happens in the cable length direction, U1, U2. But now because of the pretension, there is a support of vertical loading. This support of vertical loading, of course, is caused by the inclination of the rod or bar. So there are vertical displacement. So the association here is the tension per unit length happen along in the y direction on node 1 and node 2. Okay? So T over L0 is now becoming pre-stress stiffness. 好，所以看到没有？你如果到时候要去解题，这个老兄站在这个蓝线上，那请问支撑它的这个张力有多少 ？So now you can go and calculate how much is the difference. Okay, find out the tension. Okay, and then next. Okay, if you want to go one step further for finite deformation, you really have to find out what is the real length change. Okay, look at this. If the bar now extend so that the right tips move by U2 and going up by V2. Okay, now you can find out how much is the total length change by subtracting the right node displacement minus the left node displacement. So the vertical rise is your V2 minus V1. The horizontal displacement then is depending on this left side. Okay. So now you can see what is the cosine angle. Cosine angle change is the right node horizontal position minus the left node horizontal position divided by the length. What's the sine angle? Sine angle is then the right node height minus the left node height. Okay. Then how about the rotational matrix 2D? 2D says what you did. And then now, how much is the tension? The tension in the bar, you can do the nonlinear integration to find out this EA long starting length, final length divided by starting length, final length expressed here. Yeah. And then how much is the bar extension? The bar extension is obtained from the Pythagoras theorem. And then finally you obtain the total elongation. Total elongation is the horizontal displacement difference between node 1 and node 2 plus a square term in the horizontal direction and another square term in the vertical direction. So this is now the bar extension. With this understanding, now you can find out what is the bar tension. Bar tension is coming from linear elongations plus vertical displacement square. Okay. This is because the linear horizontal difference is much greater than the square term in the horizontal direction, but the vertical direction one can be amplified. So in this way, when you do the substitution of the previous expression, 那你如果把我们刚才得到的解数带进来，那你去做减的话，那你就可以找到